Okay, so I just got a homework question in the chat, which was asking about number one on the homework. This is showing the fact that if you have two distinct lines, and the reason for distinct here is that if you had two lines, right? So say geometrically you might not think to include this case because if you have one line and I give you another line, you're not going to draw the line over that. But for instance, say that you have two lines, but they're not given to you. Maybe geometrically they're given to you as the lines arising from, say, two equations. Then you know that even if the equations maybe don't immediately look the same, two seemingly different equations can describe the same line. Um, and so this is just to rule out the case that you have two lines that actually coincide, so they have common points everywhere. So if you have two distinct lines, then what is the condition that says whether or not they meet? That is, whether or not they're parallel. It's that they have the same slope. And so if you consider also the case of infinite slope here, the way that we did this, right, using coordinates, now that we have another way of talking about lines, makes it so that this quantity we've defined, slope, is a thing that can tell you immediately, given two distinct lines, if you know their slopes, then you know whether or not they're parallel. So you're proving that fact. And that's really the thing. The thing is use your coordinate knowledge, and the algebraic description of a line is the hint. Anyway, but also, as I was saying, I've extended the due date for the homework. It's not due until Monday, and that's so that I can have office hours for this homework set like I have for the ones in the past. So my office hours will be on Monday afternoon. So I'll make an announcement after my second class, letting you all know that. So your exam is next Friday. So I will post it on Friday, and then you will turn it in the following Monday. So this is a week from today, I will post your first exam, and it'll be due that Monday. And like I said, I haven't made an announcement about it yet, but I'll do that later. It's same rules as your homework, but you can't collaborate with other students. That's the only thing. Okay. So anyway, what we were talking about at the end last time was this legitimate construction that Italian artists used to draw a perspective view of a tiled floor. So looking at this thing, okay, we have a view of a tiled floor that looks like it is a tiled floor of equally sized and spaced tiles. Okay, even though we very much know that it's not, right? Like apparently they're getting closer together to us, right? So this might be said to be obvious if you're drawing something. So in the realm of art, this might seem obvious, but mathematically this seems a little spooky, maybe, because this is it's hard to think about, like, why is it that it looks like this, right? But like this is what it has to look like for us to say that this is like a good drawing of a tiled floor. Well, what is going on, or one way to see what's going on, is this is an exercise that you're going to be given either as part of your exam or maybe on the next homework set. So have a look at this. Suppose that you have an eye here that is fixed at the point -1, 1, and that eye is looking at equally spaced points, so the origin, the point at 1, 0, 2, 0, 3, 0, and 4, 0 along the x-axis. So these are equally spaced points. You can just see that here. But look at these vision lines, right? What do these vision lines look like? Well, even though 3 and 4 are equally spaced, when I look at this in perspective, right, with an eye fixed here, then these vision lines are closer together than the vision lines for 0 and 1. right? So that is key to what's going on here, right? So I'm looking here, and the idea is that if I wanted to draw a realistic picture of equally spaced tiles here, then as these tiles recede from my vision toward the horizon, they have to look to me closer together, meaning that if I'm drawing them from my perspective, so what my eye sees, then I have to draw them closer together, right? I have to draw them closer together or it's just not going to make any sense. So, for instance, if you tried to do this construction and you tried to like eyeball it where you were drawing this in such a way that you made these further apart than they seem, then it would throw off the perspective entirely. You would be looking at this and you would it just wouldn't look right if these tiles were too big. Okay, so this is key to what's going on here. Okay, this notion of a seeing eye, and we'll see in a second the notion of an all-seeing eye here, looking at all perspectives, is kind of the thing that defines projective geometry. Okay, now mathematically, the way that we're going to describe it, you could completely toss out this this construction and pretend that you just came up with it on your own, but there's no fun in that, and there's really no benefit to doing that either. It actually helps to see where this came from. Okay, and so I want to draw with straight edge alone. There was a thing that may be a little bit concerning about the legitimate construction. So note, the legitimate construction is actually secretly Euclidean. What do I mean by that? Remember, I wanted to investigate what sorts of things I could draw with straight edge alone. Of course, not being allowed to use my ruler here. But there's an issue with the legitimate construction. So in the legitimate construction, the starting point, just to remind you again, the starting point in the legitimate construction were equally spaced points on some line, right? Well, using straight edge alone, I can't draw equally spaced points, right? So with straight edge alone, I cannot draw equally spaced points. And so that particular way of drawing in perspective is actually secretly Euclidean in this way, because you actually require the equally spaced points. Okay. Nevertheless, it has a lot in common with exactly. I mean, one, it does use perspective, and it does introduce this idea of having a horizon line. But like I said, it is secretly Euclidean because it requires both a compass and straight edge. But we can still draw a tiled floor using straight edge alone. So we actually showed this at the very beginning of the chapter, and that's what I'm going to do here. This gives a nice way of doing this, and in fact, this is a really, really fun thing to do. I used to, when classes were in person, and when I actually used to take classes or sit through some talk, whenever I was bored, I would actually do like a version of this doodle because it's fun to do. But before I do that, I was going to introduce some terms. So some terms. The point on the horizon where a family of parallels appear to meet is their vanishing point. This is an art term. Okay. The math term is, or their point at infinity. This is the term that we're going to be using, and you'll see why we do this. The horizon itself is called the line at infinity. Okay, this consists of all the points at infinity. So this consists of all points at infinity. Okay. Now, how do I draw my tiled floor using straight edge alone? Okay, so now the pressure is on me because I have to make a nice showing of this live. So, what's the idea here? The idea is I take a horizon line. So here's my horizon. Okay, and I think that this tiled floor is going to be placed obliquely. So it's going to be placed like this, we'll say. So you look at this and you say, wait, that's not a tiled floor. That's a triangle, right? So where do the tiles come in? So here's my horizon. The tiles, well, the size of the tiles, it's what I decide. So I draw in my first tile. And to draw in my first tile, I just pick, say, a point on this opposite side, and I draw a line. Maybe it looks like that. And I do the same thing on the other side. And that is my first tile. Okay. Now you might say, all right, how are you going to draw a tiled floor out of this? So remember, we're only allowed to use straight edge alone. So in order to do this, I'm going to have to draw with pencil in some places so that I can erase the construction lines. Okay, so what's the next step? This is my first tile. I draw its diagonal. So again, I only need straight edge for this. There's its diagonal. Okay, well, that's kind of, there we go. So there's its diagonal. Okay. Then what do I do? I can do this on either side. I'm going to do it on the left side. I take what is going to be the diagonal of the second tile on the left here and extend it to the same point on the horizon. And once I've done that, I get a point where it intersects this solid line I drew that defined the upper right corner of this first tile. So once I've done that, I have this point of intersection here. I can draw another line through that point of intersection from the opposite side. Okay. So how does this help me? Well, this helps me because now I can draw the opposite side of this tile in through the other point of intersection. Okay. So, what do I get here? Well, it might be kind of hard to see until I erase the construction lines here. But what I get is the beginning of a tiled floor placed obliquely like this. Okay. All right. So I still have the remnants of these, so I could keep going if I wanted to. So here's another construction line. So I would get another point of intersection here. Okay, and then the intersection with the first line I drew gives me where the other tile should go. And again, erasing my construction line. That's the picture I have. Okay. Now, you might look at this and say, well, that doesn't quite look like the thing that you wanted to do. But actually, if you continue this construction on, if you do this for a few more steps, until basically this is essentially filled out, you will see that this gives a very, very nice picture of a tiled floor, and we're viewing it from the corner, so that's the viewed obliquely thing, right? And so ultimately, the picture that you get looks like this. Okay. So ultimately, this is what you get. That's what it looks like. So this is drawn using straight edge alone. Now, the way that for effect here, the way that this was drawn, of course, was the horizon line you can see is up here rather than along the top edge of this triangle. We could have easily done that. We didn't have to draw it so that our horizon, our floor was going off to the horizon. If you wanted it to look more like a floor and the horizon's further off, then, well, you just do exactly what I did. Ignore the fact that this is actually a triangle that I've drawn in here. It doesn't need to be, right? All I needed was that horizon line. I didn't need this to be a triangle. This was just an easy way of doing it. So this top horizon line, could have been offset, basically. Okay, and so then this is the picture that you end up getting. And this is actually really fun to do. If you want to see the full steps of this, here they are. All right, so first, once you've drawn in your first tile, draw in the diagonal. This is one of your construction lines, so you're going to erase that if you want it to look nice. Then draw in what is going to become the diagonal of this second tile over here. You could do this on the left or right. You didn't have to do it this way. So doing it on the left here, what you get is a point of intersection that you can finish drawing in three more tiles here, and you can extend this in the way that I suggested till you get something nice looking. This is actually really fun, so I encourage you to have a go at it. But this was continuing this. So continuing this yields a view of a tiled floor requiring only a straight edge to draw. Okay, so this is key. Okay, so if our goal then is to build a type of geometry on the back of, rather than compass and straight edge constructions, building them on just straight edge constructions, necessarily, right, intuitively, you know that such a geometry is going to be more primitive in the sense that the list of axioms describing it has got to be a lot shorter, right? Because you just have so much less to work with, right? Notions of angles don't exist. Notions of distance doesn't exist, right? What is the thing that is preserved? Or maybe I should say, what is the thing that that is kind of the key? Like, what can we say? If we can't, if given 2 points, I can't talk about the distance between 2 points, I can't talk about the angle between 2 lines, then what sorts of things can I talk about? So I'm going to go ahead and spoil the fun and say the thing that is left is co-linearity, for instance. So co-linearity of points, whether or not a given set of points lies on the same line. This is something that you actually can talk about in projective geometry. Okay, so this brings us to a construction of what's called the projective plane. So projective plane axioms and their models. So this is in direct comparison with, say, the Euclidean plane, right? Okay. So what do we need? So what did our construction require? We could do it with straight edge alone. Our construction required like a horizon line, right? So we need a line at infinity, the horizon. But apart from that, why does my construction work? Well, note some things remain the same in any view of the plane, which is what makes our construction work. What are these things? I say some things remain the same. What are those some things here? So straight lines remain straight. So that's one. Right? It doesn't matter what perspective our eye is at here. Right? So if I had taken this picture and I had started out with the first tile that didn't quite look like this, right? Maybe my first tile is a little bit more squished in my direction. It doesn't matter. These lines that I see as the edges of the tiles are still going to be straight lines, right? To draw them, all I need is a straight edge. I don't need anything else. Intersections remain intersections. Okay, so intersections remain intersections. Okay, so that's nice. Now, the last thing, and I didn't draw this here. You saw it in the legitimate construction, but like I said, we're going to toss that out because it requires equidistant points to start out. Okay, then what can I say about parallel lines? Well, they're either honest to God parallel, or in the cases of these parallel lines that form the edges of these tiles, they meet at infinity, right? Those are the options, right? So they're not actually parallel in the sense that they don't ever meet, right? And if you look at them, you wouldn't call them parallel in the Euclidean sense, of course, but they're parallel in the sense that the only place they meet is off on that line at infinity, so at some point at infinity. So parallel lines remain parallel or meet on the horizon. Okay, so that's the other thing. Okay. Now, again, you might look at this and say, well, how would two lines be parallel and not meet on the horizon the way that I'm looking at this? Right? Which is a good thing to notice, that if you point yourself in the right direction, then all parallel lines meet on the horizon. Okay. So, another note, parallel lines always meet on the horizon if we point ourselves and our eye, our viewpoint, in the right direction. Okay. So if we could look in all directions at once, we would see that any two lines have a point in common, i.e., if we could somehow look in all directions at once, we would see that any two lines have a point in common. Okay. Now, obviously, this is projectively speaking. In the Euclidean sense, there exist honest-to-God parallel lines. They don't meet. But thinking projectively, in terms of perspective, what this is saying is that if you include meeting at infinity, then there are no actually parallel lines, right? Any two lines meet at least at infinity. Okay, they have at least one point in common. Okay, so this leads us to the projective plane. Okay. So we are going to come up with a model for this that I describe here in a second. Okay, so this leads us to the projective plane. Okay. So axioms. For a projective plane. What are those? Okay, so first, before I list any axioms, our projective plane contains objects called points and lines satisfying the following axioms. Now, the reason why I have very much intentionally used points and lines in quotes here is that when we talk about these objects of points and lines, we are calling them points and lines with respect to projective geometry, but they're not really points and lines in the Euclidean sense. Okay, in fact, we're going to see that the points are lines and the lines are planes. Okay, or, well, I shouldn't say that. I should say that they can be modeled by those things. Okay. All right. So our projective plane contains objects called points and lines satisfying the following axioms. So, one, any two points are contained in a unique line so that is me translating Euclid's first axiom, right? So Euclid's first postulate for the construction of lines, 2 points determine a line. That is this, it's just that I've replaced points and line with points and line. Okay. All right. The second axiom, any two lines contain a unique point. Okay. So this is maybe a little strange. Okay, at first glance. So I'll explain what this says here in a second. And our third axiom, there exist 4 points, no 3 of which are in a line. Okay. And that's it. 3 axioms. Okay. So what are these axioms? Axiom 1 is Euclid's first postulate for constructing a line. So if you think about compass and straight edge construction, this is the statement that in our straight edge construction we can connect any 2 points with a unique line using our straight edge. Okay. That's 2 points determine a line, first postulate from Euclidean geometry. Just translated into our world where our points and lines are going to be slightly different. The second one, any 2 lines contain a unique point. What is this saying? So basically this says that there's no exceptional pairs of lines that don't meet. Okay. So you could define parallels to be lines that meet on a line called the horizon. And that doesn't single out a special class of lines because the horizon behaves the same as any other line. Okay. So what this is saying is that no line is exceptional. So not even the choice of horizon line. The horizon line behaves like any other line. Okay, so 2 says no line is exceptional. 3 just says there's enough points that this is interesting. Because without 3, then maybe, the projective plane you're dealing with is so small it basically doesn't contain hardly anything at all. Right? So the idea is that 3 guarantees, it doesn't mean there exists exactly 4 points having this property, but that there at least exists 4 points that have this property, no 3 of which are in a line. If you have at least that, then your space is big enough, your projective plane is big enough to be interesting. Okay. So, here's the question. We have arrived at these axioms for what a projective plane should satisfy. But the question is there a projective plane? So is there something that satisfies these axioms? This is a big question. Is there something that satisfies these axioms? That might seem like a strange question at first. What do I mean when I say is there something that satisfies these axioms? The idea here is go back to our development of Euclidean geometry. So for Euclidean geometry, we started with these axioms, right? In chapters 1 and 2, we had this list of axioms, okay? And that was all well and good working in if we're Platonists, right, then we're working in some sense, we're working in the space of forms, which is, for Euclid was the space of constructible by compass and straight edge figures. right? The question became, were there mathematical objects that actually satisfied those things? And we saw, after looking at Hilbert's axioms to look a little bit ahead, that if you threw in that last of Hilbert's axioms, you went from having the constructible objects to having the real plane in the case of Euclidean plane, or real space, R3 in the case of Euclidean space. And so those things, R2 and R3, were our objects that existed that satisfied those Euclidean axioms. So, i.e., is there some object that satisfies these axioms in the way that R2 and R3 with inner product, as we saw before, satisfy the Euclidean axioms. Really Hilbert's axioms, but easily Euclidean's axioms. Right, so this is our big question here. Okay, and the answer is yes. And that object is the real projective plane. So the real projective plane, which we write as RP2. Okay. Okay. So this is a model. Right, we've mentioned this word before. So this is a model or interpretation of the axioms for a projective plane. Okay. All right. So it defines all of these quantities that for now have been in quotation marks, points, lines, and plane, and makes sense of these axioms. Okay. All right. So what is RP2? Okay. So RP2 is the real projective plane. So take points, okay, to be lines through the origin in R3. Okay. Take lines to be planes through the origin in R3. Okay. And take the plane to be the set of all lines through the origin in R3. All right. So then, what do we note? So if we've taken this as our definition of points, lines, and the plane, what do we have here? So then any two points are contained in a unique line because two given lines through the origin lie in a unique plane through the origin. So two given lines through O lie in a unique plane through O. All right, the plane determined by those lines. Okay. Our second axiom, that is, do any two lines contain a unique point? Well, any two lines contain a unique point because any two planes through O meet in a unique line, which is a point. So any two planes through O meet in a unique line through the origin. Okay. And 3, there are 4 different points, no 3 of which are in a line. So no 3 of which are in a line. Okay. Now, what are these points? So to see this, take the lines from O to 110, or sorry, 100, 0, 10, 001, and 111. So I have 4 lines that corresponds to 4 points. No 3 of those are on the same plane. So no 3 are on the same plane through the origin. So no 3 are in the same line. Okay. So algebraically we could check this. So we could actually check. So we can check algebraically. All right. Remember what the equation for a plane is in space. Right. You can actually check algebraically that those 4 do not. No 3 of those lie on the same plane through the origin. Okay. Okay. Now, this shows us that RP2 defined in this way yields a model that is a setting in which the axioms of the projective plane are true. Now, why does this work out so nicely? So why does this work out in this way, where if we take these objects to be defined in this way, we get a nice, perfect setting for our projective plane? The reason why this works is that these strange mathematical notions of calling a point a line through the origin in R3 and a line a plane through the origin in R3, and saying that the plane is the set of all these lines through the origin, so it's the set of all the points, right? That's maybe a little bit more intuitively obvious. Why does this work? Well, this model captures the idea of viewing with an all-seeing eye. Okay. Okay. So what do I mean by this? So consider the following picture. So say that my eye is located at the origin, right? And let's say I have a plane M, which is at the level z equals -1. So we're sitting in R3. My eye is at the origin. I have a plane M. This plane M is sitting at height z equals -1. Say that I have 3 points, P1, P2, and P3, that are along some line in my plane. M is the line. Sorry, M is not the plane. That's bad labeling. So this plane is just the plane z equals -1. So I'm in the plane z equals -1. I have this line M that my points on in this plane actually lie on. Then my vision lines to each of these points are the lines L1, L2, L3, and I can continue that, of course. And as these points tend off to infinity, what happens to these vision lines? Right, so as these points tend off to infinity, out and out and out, right, along this plane z equals -1, what happens to my vision lines? Well, they tend to be horizontal, right? They're becoming horizontal. Okay. And thus, the horizontal lines through the origin, right, since they are the things that these vision lines tend to, it makes sense to call horizontal lines through the origin the points at infinity for this plane. Okay. And thus the plane of all horizontal lines through the origin would be the horizon or the line of infinity for that plane. Okay. And so this concept it can be a little bit tricky to grasp at first, but this is what's going on here. It's not always 100% apparent all of the differences that this has with the Euclidean case, but we're going to be going over all those in detail. So there is we will see that using similar ideas, we can also define a real projective line. So RP1. All right. And we're going to use the same ideas here. Another thing to note, just strictly copying. I could define RPN. Well, if I defined RP2 to be the set of lines to the origin in R3, then how do you think I would define, for instance, RP3? Right? It would be a set of some objects through the origin in R4. Okay, so I might mention some of this stuff later, but for us, of course, we're really interested in constructing the analog of the Euclidean plane for the projective case. So we're really just going to focus on RP2 here. Looking at RP1 is going to be instructive for us, though, because it's actually going to tie in together with us a notion of what exactly is going on here. Okay. So anyway, this is this is a good stopping point, so I'll stop there and we'll continue on with this. I didn't get to homogeneous coordinates. I put that in the description for the video, so I'll edit that when I move it into the playlist for the class. As I said, in the immediate, you have homework 4, which is not due tonight anymore. It's due on Monday. Instead, I'll have office hours Monday afternoon, so if you have any lingering questions about that homework, you can ask me. Then. You can also email me beforehand if you can't make it, and I'll answer an email. Your first exam is next Friday, so like I said, I will post the exam on Friday, and you'll have the weekend to do it. So next weekend. Anyway, all right. So that's the idea. So I will see you all next time. See you all on Monday.